this was the exercise. So apologies for the issues on Archer 2 on, when was it, Wednesday. The system's actually been very stable. And that's unusual. It's a shame actually that Archer 2 is the new UK national supercomputer, and that's why we're running the training. It does have this slight quirk that you can't run parallel jobs on the login nodes. You have to run them on the compute nodes. I mean, normally you run your production jobs on the compute nodes, but normally on many systems you have the opportunity to run interactively on the login node, which means you can carry on even if the compute nodes go down. It was the network, so apologies for that. But we do have a different, we have a reservation for today, so hopefully we won't experience any problems. So what I was going to do is to go through this parallel calculation of pi in some detail, because actually, although it's quite a simple example, it does illustrate a whole bunch of stuff to do with message passing programming. So, the basic, just to recap, the basic observation is that there's a very simple expansion here for the value of pi based on this integral, which is arctan of 1, which is pi by 4. And I've just done an extremely simple chunking up to work out the area under the curve with a lot of bar. You should use Simpson's rule or something here. It's very, very simple. And so what I'm going to do is I'm going to run this on Archer. So I will share my Archer screen, and this will double check that things are actually working correctly. So you should be able to see my okay. Whoops, something happened there. Sorry, something weird happened there. Okay, so I'm logged on to my account. I want to get the material, and as you can wget, but there's this weirdness with Git where you have to replace blob with raw when you cut and paste the URLs. I find that very annoying, but there we are. I'm in /work, and we can unpack the mpp pi.tar. So actually, I should just maybe do a quick so I can go through this. They're very completely the same, the C and the Fortran solution, but I know I did a poll on the first day, and it was largely C, C++ programmers. I just wanted to check what we were just now. Any more people want to vote? We've got most people responding already. Okay, so actually most people wanted the Fortran one, which is fine. I'll go through the Fortran one. I'll do the C one. I'll do them all, but I'll do the Fortran one first. So that's useful. Okay. Okay, so I'll go to the first is the Pi serial. It's just important to notice. Very, very simple example. I just do this, and I do this loop here. This would look exactly the same in C, except in C you don't have this nice power operator here, and in C most people get this wrong. It does go from 1 to n. This is not just a counting loop. The value of I appears in here, and you need to be careful about casting. So I'll just compile this just to show you what you. So I should do ftn -o pi serial.f90. and I get 3.1 for 1592. It's pretty accurate. The biggest mistake people make when they do this is that they do something. So I've computed the exact value here, but the biggest mistake is people do something like this. Okay, that's what will I get if I? What's the answer I'll get if I do that? Do they want to guess? This is why I tell people to write the serial program first. It's quite easy to get this wrong. Exactly, 0. You'll get 0 because 4 divided by n is 0 in, if let's just okay, no, pi, okay, so in Fortran, actually, okay, that's weird. Okay, so Fortran, I thought that would give me, so Fortran is doing something more clever here. It must do a different promotion. Maybe if I do that. Anyway, this is slightly of diversion. Yes, okay, it was the bracketing. So it was doing the, okay, fine. So now let's look at the parallel version. So program pi parallel. So I use MPI, okay, and I do implicit none, of course. This is all the stuff I have before, but now I have some MPI variables. I have my com, rank, size, source, tag, and I-error, and I have my status, which in Fortran is a little array of size MPI status size. Again, that has to be an array. In C, it would be it's a little structure. Now I have some other local variables, and the obvious thing to do here is just to simply reproduce the code I had before, but instead of going from 1 to n, go from I start to I stop, where I start and I stop depend on what rank you are. And then I do double precision partial pi, and I have a couple of extra variables here, and I do a print here. And if you note, this print is before the MPI init. Okay, this print is, and that's again to try and emphasize the way that the MPI works. I do this trick of do com equals MPI com. I think that's a bit neater. The normal stuff and write hello from rank whatever, but actually we normally want to do only, so this is just the normal stuff. Okay, now here we are. So computing a cross matrix pi using a simple series expansion pi by 4, just to be, so I take the iteration space of size n and divide it into size chunks. So if there's 4 processes, each of them gets a 210, and then I work out where to start. And so rank 0 starts at 1, rank 1 starts at n over size plus 1, etc., and do this I stop here. And it's important. I mean, I don't really have time in this course to talk about debugging, but you know, one of the most powerful tools you have for debugging is print. Okay, this code will only work if I start and I stop are correct. It's very easy to get them wrong. This +1, -1, just print them out. Okay, and you have to print out what rank you are, because of course these values are different. And this illustrates SPMD now, single program multiple data. Every process runs the same code, but they don't do the same thing because the I start and I stop are different on each process. Remember, although I've got integer I start, integer I stop, every process is independent, independent program. Every rank has its own values of I start and I stop, and I have set them based on the size and the rank, until they're rank dependent. And now I print out the partial value, and that's quite, so this illustrates SPMD. Now I want to compute the sum, and it's very important to note, I've said here, you know, note this would be more efficiently done using MPI reduce, which is a collective operation, which we'll cover this afternoon. Yes, we'll cover this afternoon. But what we're going to do is, the first thing we do is, well, if rank, so what we do is we nominate a controller process. Now I've chosen rank here. People typically, if you do have a controller process, a process that wants to do something special like print debug messages, we normally pick rank 0. There is nothing special in MPI about rank 0. But conventionally, if we want a controller, we always pick rank 0. Why do we always pick rank 0 if we want a controller? It's just a convention. It's a useful convention. We want to remember, we want to write MPI programs that run. It works for any number of CPUs. Exactly why? I mean, I think you've got the answer. Rank, there is always a rank 0. Absolutely, there is always a rank 0. So convention, but there is nothing special about rank 0 in MPI. So first of all, if I rank, so now we have this split where again SPMD, single program multiple data. One of the ranks, rank 0, is doing that branch, but the rest are doing this. So all other processes and their parts. So I've actually put this thing into partial pi here. Okay, I've called it partial pi, not pi, because it's initialized to 0. So all other processes. So I've done a print here. Tag 0. I'm not using. I've got a variable for tag, but I've just MPI send the partial value of pi, which is 1 MPI double precision or MPI double in C, to rank 0, tag I error. And that's synchronous send, and so that process will wait until the receiver's been on. Now, so there's only one line of code here, okay? But how many sends? If I run this on 8 processes, how many sends will there be? So there's one line of code here. It's not obvious, you need to understand that when I run that program, how many sends are called. Size -1, not size, it says 7. Okay, all processes bar rank 0 go into here, and there are size processes. So if we have size -1 sends, then the controller needs to explicitly do size -1 receives, and that's what we're doing here. So we individually map, every send has to be matched by a receive. So the controller has to explicitly say, I'll receive from you, I'll receive from you, I'll receive from you. So we initialize our pi to our partial value, and then we do all these receives. So we want to receive the receive pi. I've called it receive pi. I could have called it pi, but partial pi, but which is 1 MPI double precision from, and I've got MPI any source here. So I'm receiving from anybody. Tag is 0, so it will match. Com status I error, and the reason I've done wildcarding is to illustrate how the status works. Rank 0 says receiving from rank status MPI source. So this status will be filled in with the actual message which came in, and we don't know who it's going to receive from. And then I print out what it is, and I do a running total. And then at the end, I just print out the value at the end, exactly the same, and I finalize. And I've used slightly shouty capital letters here for MPI. You don't have to do that. I don't normally do that, actually. So let's compile that. Now we're going to have to copy the Archer 2 MPI template. What was it called? Archer 2. And I'll do 4 for the sake of it. And the reservation today is this number here, TO31, not 129. And I don't want to do /pi parallel. So I can now run that. It's run. And we get the output here. So, okay, so we got computing approximation to pi using n equals 840. So the important point is that we get this message computing. Now, for some reason, what the runtime system done here is it seems to have appended, this is the output from rank 0, this is the output from rank 1, this is from rank 1, this is output from rank. They're normally interleaved. What I will do actually is I will run this code interactively. But the most important is we get the right answer. Okay, there's our pi. Pi is this and the error. So we get the same value for pi, 3.1415928. But I would rather do it. So if I do an S run, I would rather do it interactively, and that's more illustrative. That's 131. Node equals 1. Pi parallel. We will see that, yeah, I'll actually do that at the top of the screen. There we go. Okay, so this is more like what I'd expect. We get these 4 computing. So the important, I put that print statement before MPI init to make it clear that there are already 4 processes running before I call MPI init. Okay, and then if we look, rank 0, I start. Now this is 1 to 210. That's correct. That's correct. That's correct. And the important point is here that rank 0 received from rank 312 in that order. That order is not guaranteed 312 because, of course, the next time it might do a different order. It did 231. Okay, so the output, the order of these outputs on the screen don't have any significance. It doesn't. This hello from rank 2 didn't necessarily happen before this hello from rank 1. Who knows when the messages appear on the screen? But from an individual rank, and this is rank 0, these are significant. You know, these appear in the order they were printed, so it came around in a different order. And of course, you will see here that if I now run on, say, let's do 32. Does 32 work? Let's do 20. And I'll just, that's going to be too much output. So what I will do is I will just, I'll just get the answer out here. So I'm running on 20 processes and I get this value of pi. I run again and I get the same value, but I got a slightly different value here. Okay, I've run the same code twice. Okay, but got different values for pi, very slightly different values for pi. Why is that? Does anyone hazard a guess? Yes, so exactly. Adding floating point is order dependent, absolutely. Floating point. Well, yeah, we can call them errors all round, but floating point arithmetic is not exact. Computers aren't doing maths, and of course, what we're doing by doing MPI any source, we're doing a first come first served. We're saying, you know, whoever finishes first, I'll add the answer in. We can fix that if you want by doing. At the moment, all I'm doing here is I'm saying I want to do size -1 receives from anybody, but I could mandate that they came from, instead of MPI any source, I could receive them in a particular order. I could say source here. Okay, and now that's a defined order. And so if I now compile, yeah, and I do the S run again, I should get the same answer each time because there's a defined order. And in fact, if you look, if I look at the output, you'll see, of course, not surprisingly, it is receiving them in the right order because that's what I've mandated. So that's really all I wanted to say about that. So this looks, you know, this may look like a fairly trivial program, but it's really, you know, it's not trivial to get this right. The fact that this works requires these size -1 receives to be matched by size -1 sends. And that happens because one process goes here and explicitly does size -1 receives, and size -1 processes go here and each do an individual send. So for example, if I get any of this wrong, for example, if I do that and I compile, what will happen now is I will, if I do the S run again, let's do 4. A bit easier to see. You'll see that I get the wrong value for pi, and my program hangs. So remember what I did there is I missed out one of the receives. So why is this hanging? I've issued only 2 receives instead of 3. So not surprisingly, I get the wrong answer for pi because I haven't added in the contribution from rank 3. But why is the program hanging, deadlocking? Yeah, so the blocking communication on what, Alex? You're right. You're absolutely right, but just to check, the S send, yes. So rank 3 is doing an S send and it's not being received. Okay, and equally, so yeah. So you know, again, simple programs. That's why running interactively is nice, because if I'd run this in batch, I'd have just seen my. Oh, okay, doesn't really like that very much. That has gone now. So are there any other questions about that? What I'll do is I'll go through I'll go through the other versions very quickly, just to. Are there any questions about that? It's quite a simple program. It does illustrate a surprising amount. That's why I quite. Okay, so if I go to the C version, it's exactly the same. Except we have to include math.h because C doesn't know about maths, include MPI.h, The MPI variables here are typed, so it's MPI com, MPI status, status. All the rest is the same, except, yeah, the loop here. I have to be a bit more careful and see I start, less loop to I stop. Be more careful about my pow command here, but it's exactly the same. And then when I do the send receive, the only difference here is I'm receiving. I have to do a pointer because I need a pointer, but the sender is status.mpi source. That's the only difference here. So it's exactly the same code. I have showed the C++ version, but it really is I'm not a C++ programmer, and all it does is it just shows you. All I've done is replace printf with cout. So, I mean, that's really just there. The only reason I've really included this is to show you how to compile it. If I look at the make file, there's actually the C compiler is called capital CC. So, for those who are Fortran programmers, the Fortran 2008. So the nasty thing about the C and the Fortran interface for MPI is that everything, communicator, tag, data type, they're all just integers and they're not parameterized, and that makes the compiler's not doing as much work for you there. The more modern interface, the 2008 interface, as I said, it's not so heavily used, but I would you should think about using it if you're a Fortran programmer. You have to use a different module, use MPI FO8 because it does have a different interface. Now, the main point now is that the Fortran 2008 interface is just the same as the C interface. So instead of saying integer MPI, integer com, use the C syntax, or the equivalent in Fortran, type MPI com, type MPI status. Okay. So really the only difference here. The other difference is you don't need the IRA variable because you can omit it, and Fortran allows. You can put it in if you want, but you don't have to specify it. And the status is now, just like in the C version, the status is here. The status is a member of the structure, status %MPI source, or the derived type in Fortran. Exactly. So there is some slight complication here. I don't want to go into it now, but Fortran also has a very sophisticated typing system. You don't say double precision or whatever. You say, I would like a variable which is so many, which is accurate to a certain level, and the compiler will give you a variable of that type. So you don't know at compile time how, in principle in Fortran, you don't know at compile time how big your variables might be. You don't know if your doubles are, if your floating point numbers are 4 or 8 bytes, depending on what the compiler decides to do. But there is a way of doing that cleanly in MPI, and I've illustrated it here. You can inquire at MPI how big a type is. It's called MPI type size of an MPI type match size. So this allows us to define at runtime, rather than hard coding MPI real or MPI double precision. It allows us to inquire at runtime. Give me a type. This is saying basically, give me a type which matches this pi variable. That's slightly over the top. So that's really all I had to say. Are there any other questions about that? It's quite a simple example. It is worth it. I think it does illustrate the key points of SPMD and send receive. So the classic example we're going to think about is where we have deadlock. Now, this is the communication pattern that we wanted in the traffic model. The numbering here is slightly unusual, but we have a bunch of here 1, 2, 3, 4, 5, 6 processes. Okay. And they're arranged in a ring, where each process sends to its neighbor, but we close the ring. And this was the equivalent in the traffic model of having a roundabout rather than an open road with periodic boundary conditions. And it's very, very important to realize that you have the danger of deadlock here, okay? Because if you program with synchronous send, if everyone issues a receive first, then by definition, no one is sending because everyone's trying to receive. They're not going to progress onto the next line of code until they've got a message. And so if you program this as receive from one direction and send to the other, it will deadlock. If you program it as send in one direction first, then receive in the other, you've also got the danger of deadlock because if you use synchronous send, that is guaranteed to deadlock because everyone is trying to phone their neighbor and nobody is receiving from down the way. And if you use standard send, as we said, there's a danger that standard send might be synchronous. So it's really, this is the communication pattern we're going to use for this exercise, the exercise associated with this lecture. But it's important to realize this is also the communication pattern in the traffic model, and it is a very common communications pattern in real codes. So that's if you program this up naively, you will there's a danger of getting deadlock here. So the mode we've talked about before is a formal definition of when it's of when a communication completes. That's synchronous or asynchronous. So synchronous communications don't complete until the message has been delivered. Asynchronous communications complete immediately, or once there's been a copy taken. But so normally you would think that that would be the same thing as when the function or subroutine returns control to you. When you call, if I call a square root operation, y equals square root of x, I expect that when control returns to me, that square root is being computed. However, we'll see that the MPI has something it calls the form, which is blocking or non-blocking, which determines when the procedure implementing that operation will return, when control is returned to the user program. And what non-blockings do is that they initiate a communication, but don't wait for it to complete. They return control to the user program immediately, and that allows you to do other things. In particular, allows you to break the deadlock. Now, the terminology is slightly confusing because in other contexts, you may have called this asynchronous operations. But in MPI, synchronous and asynchronous refers to whether whether you wait for the receive to happen or not, whether the function implementing that returns control to you immediately or not is called blocking or non-blocking. So blocking operations only return from the subroutine call when the operation is completed. These are the routines you've used thus far: MPI send and MPI receive. So when send returns, we know the message has been delivered, which requires there to have been a receive posted. When a receive returns, we know that the data has arrived. Non-blocking operations return straight away. So if we look at my operation for sending a fax, what I did previously was I put the fax in the machine and I waited till I got the beep, which meant the fax had been, and I stood there potentially forever, waiting for acknowledgement the fax had been received. What a non-blocking operation does is you initiate sending the fax. You are then so you have separate initiation and test or completion or wait calls, and because there's different function calls in the middle, you can do other useful work. And I've shown myself pulling a lever here, but actually we will see that you can also do other communications. And in fact, in practice, what you do in this, when you've initiated one communication, you might initiate a send to your neighbor. You then control returns to you immediately. You can then issue another communication, maybe a receive from your downward neighbor. So in practice, although people think, oh, this allows me to overlap communications with computation, in reality, this is mostly used to break deadlock, to write communications in a way which they're guaranteed to finish correctly. So it's really important. All non-blocking operations should have a matching wait operation. If you initiate something, you have to come back later and say to MPI, I'm going to wait for that communication to complete. If you don't, you get the equivalent of a memory leak. And people often, it's a very common thing that people do. They forget to do that. The important point is that non-blocking operations are not magic. People often use non-blocking operations in their code and say, oh, well, I'm not going to get deadlocks, I can use non-blocking. No, they're not magic. A non-blocking operation immediately followed by matching wait is equivalent to a blocking operation. The point is, because you have the initiation and the completion, the initiation and the wait for it to complete as separate function calls, that allow you to pull them up, do something else in the middle. But it's really important that you realize it gives you the opportunity to do clever things like break deadlock, but there's nothing magic about them. And of course, there's a slight subtlety. These aren't normal sequential operations because the operation continues after the call has returned. You're asking MPI to start doing something, and that will go on in the background. And so there are some subtleties which I'll cover on Wednesday related to do that with that. So it separates non-blocking communication, separate communication to 3 phases. You initiate the non-blocking communication. It doesn't block or wait for it to complete. It returns control to you straight away. Then you do some work, perhaps involving other communications. And in fact, that's the most useful thing to do. And then later, when we say, well, we can't go any further until we know the communication is completed, we wait for the non-blocking communication to complete. And so a blocking send, a non-blocking send, is a bit like having an outbox. It's a bit like, I would normally send a message in MPI. I say, this is my message. I would say to MPI, please deliver that message. And if it's synchronous, I'm standing there or on the phone waiting for it to forever, potentially for it to be received. What I do in non-blocking operations is I say, it's a bit like having an outbox. I say, there's the message, okay? In this, go and deliver it, and I'll come back later and see if it's been sent or not. The important point is the reason there is the difference between non-blocking and asynchronous is quite subtle, because they both achieve the same thing. They allow you to avoid deadlock by returning control to you, the user, before the communication is necessarily completed. But there is no copy taken. Okay, the way that the asynchronous communications work in MPI is there is a copy taken of the message. For non-blocking, there is no copy taken. And that's the important difference, and we'll come back to that. So non-blocking send is a bit like having an outbox. Non-blocking receive is almost identical to having an inbox. So if I issue a normal blocking receive, I say, I'm expecting a message, could you place it there? And I wait forever, potentially. With a non-blocking receive, I say, look, I'm expecting a message, put it there when it comes in, and I'll come back later and check if I'll see if there's a message in there. Okay. So and that's a very useful pattern, because if you have a sort of a controller worker setup where I've sent out tasks as the controller to all you guys to work on, why shouldn't I be doing work myself? In the original thing, I would issue a receive from MPI any source and wait for some data to come in, but that means I'm doing no work myself. Why don't I issue a non-blocking receive, an inbox, from MPI any source, and periodically check to see if a message has come in? And this is what you can do that with non-blocking communications. And so the handles for non-blocking communication are, we have an MPI data type, or they're the same, a communicator, but we also have something called a request. A request handle is allocated when a communication is initiated. And the best analogy, I think, actually non-blocking communications are a bit like sending a message, a parcel with a courier. So if you want to send a parcel with DHL or some other courier, you go to an office potentially, you take your package and you hand it over to them at the desk and you say, here's my package. You give them the package and you give them some money. They give you something back. Okay? So you've paid them, you've given them the parcel. You're sending a present to your auntie in Australia. You've given them the parcel, you've given them some money, but they give you something back. What do you get back from the courier, having given them money in your parcel? What do they give you? A receipt, exactly, but what does it contain? That's just about right, but a tracking number, exactly. They give you a tracking number. And MPI calls this the request. And so the tracking number uniquely identifies that message passing operation, and it allows you to phone the courier up or go online and say, has this parcel been delivered yet? So and it's up to you to remember that tracking number. If you forget the tracking number, you can't track it. So when MPI initiates a non-blocking communication, a send or a receive, it gives you back what it calls a request, which is a ticket of tracking number you have to remember, and that allows you to later on say to MPI, see this operation associated with this tracking number, with this request, has it finished or not? So you have to remember these requests. And so the prototype is very similar. It's exactly the same as a normal send, MPI IS send. So I stands for immediate. So the non-blocking forms have an I in front of them, which is supposed to indicate they return control to you immediately, or they just initiate the operation. Buff count data type desk tag com, exactly the same, but MPI gives you back a request. You don't go to the courier and say, send this message and I want it to be partial. I want it to be partial number 5842. They give you back some meaningless tracking number. Okay, and MPI does the same. Same in Fortran, except it is an integer. In Fortran, the request is an integer. You can then later on wait and say, okay, I can't progress any further, so I know this message has been delivered, so I will wait for this request to be delivered. Now, there's also a status parameter here, which I'll come back to. So what form does what take? The request. You don't know the track. Well, you just get a request, and it doesn't mean anything to you, but it means something to MPI. Just like when you open a file and see, you get a file pointer or a unit number. You get, it's just a thing. It's just a reference, and it refers to some internal MPI data structure. So you can't do anything with it, but ask MPI, has this finished? Does that? I mean, it might be an integer. I don't know what it depends on the implementation, how it stores it. But it's the unique identifier that MPI attaches to that communication. Is that? Yeah. So it's what they call an opaque object. It refers to that communication, but you don't know. It doesn't have any meaning in itself. Okay. It could just be a number. I don't know. We need to look at the implementation. So now, if I issue a send, then a wait, I've achieved exactly nothing. If I issue this send and this wait, that's exactly the same as the blocking operation. But the fact is, because they're different procedure calls, it allows me to put code in here. This gives me the opportunity to break the deadlock if there's deadlock. But as written, this code achieves exactly nothing. No, the request isn't there. It's like, it doesn't mean it's a request. It's a type MPI request, or in C it's of type MPI request. You could look at the header file to see what it is. It's probably a structure. I don't know, but MPI doesn't define that. Why do you care? It gives you something. You can then give it back to MPI and say, has this communication finished? Yeah, I don't know what it is. It's a request, which MPI understands. So in Fortran it's an integer. In C, it's a variable of type MPI request. How that's defined, I don't know. You could just look in the header file if you wanted. Okay. So non-blocking receive is very similar. MPI receive, buff, count, data type, source, tag, com, and it gives us back again a request. Now, there's only one request type. MPI remembers internally if it's a send or a receive request. There's just a request. Now you'll see something is missing in this. So the additional parameter to this MPI iReceive as compared to MPI receive is this request, which MPI gives you back. Okay, but there's something missing from this receive, which we have in a normal receive. The status, exactly. So why can't MPI why doesn't it make sense for MPI iReceive to give you a status? Why doesn't that make sense? What does the status tell you in a receive? Yes, it's not completed, exactly. So the point, the status in a receive tells you what message actually came in, who it's from, how big it was. By definition, when the MPI iReceive returns to you, no message has been received. That is why the status is deferred to the wait. Okay, this says wait for this request, which turns out to be a receive request, to complete, and when it completes, the status will be filled in. So if you think about it, you have to defer filling in the status to the wait. So MPI waits the block. It says wait. Do not go any further until this communication has completed. And when it completes, it will return to you and it will fill in the status. Same in Fortran, except the status is a little array here. So send and receive can be blocking or non-blocking. A blocking send can be used with a non-blocking receive and vice versa. MPI doesn't care. When it's in the network, a message is just a message. You can use non-blocking sends for synchronous, buffered, or standard, and the synchronous mode effect has an effect when the communication is defined to have finished. But I'll just give you. So these are the four commands. So if you use synchronous send, you run the danger of deadlock. So we often use MPI IS send, the non-blocking call. Equally, we can try and break deadlock by using non-blocking receives. I receive. Because standard send can be synchronous, and it may be synchronous, as we explained in the communicators, tags, or modes lecture, to write safe code, if you use standard send, you probably often have to use MPI send to guard against the fact that standard send might become synchronous and wait for there to be a receive. This routine exists for completeness, but it's pointless. You would never use it, because if you use bsend, you don't have any problem with deadlock because MPI is taking a copy. So MPI bsend is there for completeness, but it's a useless routine. You would never use it in practice. There is no need. It has a meaning. Okay. Oops, it's dropped mine. When bsend, not when MPI bsend returns, what is guaranteed to have happened? When MPI send returns, it's guaranteed that the message has been delivered, at least started to be delivered. When MPI bsend returns, what is guaranteed to have happened? It's not guaranteed the message has been delivered, but something has happened. A copy has been taken, absolutely. So in principle, MPI bsend could return control to you before the copy is taken, but it's of no use. Okay, so yeah, a copy exists exactly. So you can actually you can test. So you can actually in that controller worker situation where I said I would set up a non-blocking receive for the messages to come in. Waiting isn't any use. I don't want to wait for a message to come in. I want to check if a message has come in, and that's MPI test. So MPI test it returns a flag which is true or false in Fortran, or 1 or 0. So I'll come back to good questions. Someone's asked about MPI wait. Yeah. So MPI wait, MPI test tells you if there is a message there. So for a receive, it will say, has a message come in? And if it has, it will give you the status. But if the flag is 0 or false in Fortran, it says, no, it hasn't. And if you're waiting on a send, it will say, if you test the send, it will tell you whether that data has been sent yet or not. So the important point, so Dilhan, does MPI wait know whether it's waiting for send or receive? Yes. MPI remembers. So it's up to you to remember. To write a correct program, you need to know whether this request is a send request or a receive request. Typically, you call them different names, but they're of the same type. And yes, MPI remembers whether it's a send, because this refers to that communication, be it a send or a receive. MPI will remember ticket 8542, that was a send. Okay, so that, yes. And does it matter? Yes, it does matter. It matters. Well, yeah, to write a correct program, you need to know what you're doing here. You need to know, am I waiting on a send or a receive? Because the logic of your program will depend on that. Does that make sense? Okay. Yeah, okay. So if we give an example here, so obviously if you issue a test on a receive and it says yes, that receive is completed, you can then read the data. But if you issue a test on a send, and that, why would you need to know whether a send has gone or not, or need to wait? If I have imagine I was why is it important to me to know whether a send has completed or not? It's important to know if a receive is completed or not, because only when the receive is completed can I read the data. But why is it equally important for me to know when a send is completed? So I've said to MPI, please send that data. Here's a megabyte array. Send that data. Okay. Why is it important if I do that in a non-blocking way? Yes, exactly. You want to know if you can edit the data. So you must not touch the data. Okay. So if I say to MPI, please send that message, and then I alter it, I don't know if MPI sends the old or the new version. So it's exactly right. This is one of the situations in MPI where you get relatively subtle race conditions, runtime race conditions, which you often get in threaded programming, but not often in message passing, that if you alter the data, if you don't check whether a communication is completed or not, and you edit the data, you get unpredictable results. So yes, at some point you're saying, I'm going to need to reuse that buffer. I'm gonna have to wait until that data's been sent. Okay, it's been sent. Now I can reuse the data. I can edit the data, absolutely. So just a simple example, slightly contrived, but just to show you this, I'm going to give the C example here. I want to send the send array from rank 0 to rank 1. You would obviously normally do this with MPI send and MPI receive, but for unspecified reasons, I've decided to do it in a non-blocking way here. So I do MPI request, MPI status. If rank equals 0, I want to send this array, which is 10 integers, to rank 1. But because I do it in a non-blocking way, I get back a request. So this then initiates this send. I then say there's a routine called do something else while I send happens, and I do something else, and then I say, look, I can't do anything more, I have to wait for it to complete, and I wait on the request with the status. Now, for a send, the status isn't particularly useful, but we have to put it in. Now, it's very important that, okay, I'll come back to that. On the receive side, again, instead of doing a blocking receive, I say, well, I want to set up a receive, I want to initiate a receive of 10 integers into receive array from 0, and I get back a request, which then identifies that receive. I do something else while I receive happens, and then I say I can't do anything more, and I wait for that to complete. So this transfers the data from send array on rank 0 to receive array on rank 1 using non-blocking communications. But I just wanted to give you some actual code. The very important point, though, that this request is a send request, and this request is a receive request. But I only have one MPI request here. But why am I allowed to simultaneously use it for a send request and a receive request? I'm asking quite a simple question in a very complicated way. How many requests are there when I run this program? There are different processes, exactly, Matt. So there are actually 2 requests, and I've decided that rank 0 will use this. So this wait doesn't wait for the end-to-end communication to finish. This request does not refer to the end-to-end. There's no such concept in MPI, really. This refers to the send part. When I wait on this, has my send part completed? Yes. This wait, which is issued on rank 1, says has my receive completed. So you're waiting here on the send and independently here on the receive. You're not waiting on, in some senses, the end-to-end communication. That's sometimes a model that people have. In Fortran, it's exactly the same, at least in Fortran 2008, Fortran 90, except the status is an array and the request is an integer, but the code is exactly the same. Now you can have multiple non-blocking communications. You can have, I might have. I said in this controller worker situation, I could set up a non-blocking receive from MPI any source, but I could equally have set up, say I had 20 workers, I could have set up 20 non-blocking receives, one for each worker. And then I would want to say, look, I've got these 20 receive boxes, I want to wait for them all to complete. I want to wait for some of them to complete. I want to wait for it. And there's lots and lots of differences here. So there are routines to allow you to test for the completion of multiple non-blocking communications, and you can do wait or test for completion of all messages. Okay, MPI wait all or test all, and now you start to have. I'm not giving the prototypes here because they're quite long and verbose, but it's kind of obvious what's going on. We supply an array of requests and an array of statuses, and wait until all have completed. Test if all have completed, and return a flag. So this is saying, have they all? I can test or wait for completion of one message. I can say, look, you supply an array of requests and a single status, and wait until one is complete, or test if any have completed and return a flag. And it also returns an index. So when you do wait any, you're saying, I want to wait for any of these to complete. And MPI will say, yeah, one of them's completed, and by the way, it was number 5. So you have lots of arrays for requests, and you can do test or wait for completion of as many messages as possible. This waits for all of them. This is for one. This is for some. So you have an array of request status indices, and you get the parameter count gets quite. But what you're saying here is you're saying, look, I've got 20 outstanding non-blocking receives. Could you tell me which one of them have, how many of them have completed? And MPI says 5 of them completed, and its numbers 1, 7, 12, 19, 23, and whatever. So you need to look up the process, but those routines exist. So if you ever have, when you have multiple non-blocking communications on the same process, you need to remember multiple requests. Okay? The biggest mistake people make is they overwrite requests, and then of course it's like losing your ticket number. This is just a convenient place to mention this routine. If you have a very simple communications pattern, one sender, one receiver, like the message around a ring, which is the communications pattern in the traffic model, the reason you get deadlock there is if you issue this receive first, you might never get to the send. If you issue the send first, you might never get to the receive. MPI does provide a routine called MPI send receive, which basically allows you to specify all the parameters for the send and all the parameters for a receive in the same call. So you do see a lot of people using this call. I'm not particularly a fan of it because it can break the deadlock in simple pairwise communications patterns, but it's not as generally applicable as non-blocking. And so I would recommend not using this routine, but you can use this routine in simple situations, but I would recommend if you're going to want to learn to program an MPI, you should learn to use the more general non-blocking communications. Actually, if you look in the library as to how it implements send receive, I bet you all the library does is issue a non-blocking send, a non-blocking receive, and waits for them to complete. Okay, well, that would be what it does. So it's not magic, and you should learn, although it's useful in simple situations, it doesn't generalize to more complicated communications patterns, at least not generalize elegantly. And so I would recommend you should learn how to use non-blocking communications. So the exercise is to rotate. So yes, wait can wait forever. Okay, wait can wait forever, but it allows you to write a program. I mean, that's actually what the exercise is going to do here. Yes, if you do a wait and there is if you wait on a receive and no message ever comes in, then if you have an incorrect program, it will still deadlock. But it makes it much easier to avoid deadlock. But yes, wait can still wait forever, exactly the same way as a send can wait forever or a receive can wait forever. Now, what we're going to do in the exercise, I will probably actually, the exercise is quite simple. In the Pi example, we did a global sum, a reduction operation by everybody sending their answer to a controller process. We're going to do the same thing here, but we are going to implement it by everyone. I'll show you the exercise. This is it. Rotating information around a ring. What we're going to do is we're going to add up all this. We're going to get a bunch of integers, and we'll just use our rank, and we're going to add them up rather than sending them all to a controller process. We're going to implement this message around a ring pattern. So what we do is we send the data around a ring, like passing buckets down a chain, and if 4 integers, after 4 steps, we've sent all the data around and everyone can get the correct answer. So I'll come back to this, explain a bit more detail, but this is just there to illustrate how to program up this sending a message around a ring pattern safely and avoiding deadlock. And we do it with this simple example, but it is a pattern which happens a lot in real programs. As you've seen, it's already arisen in the traffic model. And so the exercise, I'll maybe go through the exercise in a bit more detail. Well, there's an extra slide here. So the notes are okay. So if you think about this pattern, which is sending data around in a ring, there are a number of ways of doing it. Okay. One way is to do a non-blocking send to your forward neighbor. Sorry, I've got this. So I'll just check I'm on camera. So if I'm sending data, what I do is I say, here's the message I want to send to my forward neighbor. Please send it. I immediately turn around and issue a blocking receive to my backward neighbor, which matches their non-blocking send. I then go back and wait for this forward send to complete. Equally, I could do the opposite. I could say, well, I'm expecting a message from that guy there. I'll issue a non-blocking receive. So please, then I will say, I'll do a blocking send up the way. That completes because it goes into their non-blocking receive. Then I can turn back around and wait for the message to come in here. Or more elegantly, I can just do a I can say, look, send that data up there, receive the data up there, and I'll just wait for them both to complete. Thank you, they're both over. Non-blocking send to forward neighbor, non-blocking receive from backward neighbor, and then or you can do the most elegant thing is to store these in an array and do a wait all. Non-blocking send, non-blocking receive, tell MPI, wait till they're all completed, and then I can go on to the next iteration. So it's a relatively straightforward example, but you do need to think about it and be very clear. And the thing which people get wrong from experience is your neighbors don't change. You know, you send to the, well, I'm saying send to the left, receive from the right. If I'm rank 3, I send to rank 4, receive from rank 2. I then send to rank 4 and receive from rank 2. I keep doing that till the data has gone all the way around the ring. So that's the first thing. You do not alter the data you receive. You receive it, you add it to your running total, and you pass the data unchanged along the ring. You don't keep passing your rank along the ring. You don't pass the running total along the ring. You're just getting this data and adding it up. And this is a point which someone's already mentioned. You must not access send or receive buffers until the communications are complete. You cannot read from a receive buffer until a wait on an I receive. That's obvious. But you also cannot overwrite a send buffer until after a wait on IS send, because otherwise you might be overwriting the data before you sent. So that's the end of that. Like, are there any questions? I'm happy to take questions. I'll start the recording. So what we're going to talk about now is collective communications. So if the previous two exercises, the pi example and message around a ring, both implemented a reduction operation. I did not. Now, in practice, if you want to do a reduction operation, which is a very common thing to do in scientific and technical programming, you should use MPI's inbuilt reduction operations or collectives, which we're going to cover in this lecture. However, they are the reason that we do those exercises is they are very, very important to get the concepts, and the message around a ring is a perfect example of when you need to use non-blocking communications. Although in practice you wouldn't be doing it for doing a global reduction, you would be doing it for halo swapping in something like the traffic model. It's just that doing a global sum of the ranks is something that's a useful training exercise. So what I'm going to talk about here are collective communications. So collective communications involve a group of processes. Point-to-point communication has one sender and one receiver, but collectives are involving a group of processes. They call back all the processes in a communicator. Now, again, we will just use typically use COM world here, but they do have the flexibility for doing communications across subgroups. And the examples are barrier, broadcast, scatter and gather, and global sum, global maximum. I'll spend most of my time on these, because these are really the crucial ones in scientific and technical programming and that affect the performance of your code. You'll also see, if you look to the exercises, that there was an additional exercise to implement a scatter or a gather, I think it's a scatter, using MPI point to point. That's there again as a training exercise, but also as a way of making it clear what the communications pattern is. That's why that exercise is there. So the characteristics of collective communication, it's collective across the communicator. All processes must communicate. By communicate means they must call the collective routine. So the biggest mistake people make is that they say if they want to maybe do a broadcast or a reduction, they say if I'm rank 0, then call the reduction operation. That's never going to work, because everyone has to take part in a collective communication. As I will see, within that collective, you may have different roles, but you all have to call it. All processes must communicate. Synchronization may or may not occur. This is a slightly technical point, but in my mind, I think of collectives as being a barrier. Everyone does their stuff, another barrier, and then finished. Then barrier may not be there depending on the collective, but that gets across to you if that's your mental model, that inside the collective, not you, inside the collective, there's a barrier so everyone's ready, they do their stuff, and there's a barrier so everyone's finished. That gets across the fact that if some of the processes don't call, then you could get deadlock, because not all the processes are calling the barrier. Standard collective operations are blocking, Non-blocking inversions have been, I say recently, have been introduced into MPI recently. They're just, I don't cover them here, they're just the obvious extension. There's an extra request parameter, but in practice they tend not to be that useful. There's no tags, and the receive buffers must be exactly the right size. So MPI, in point-to-point, MPI does do some checking about the receive buffers being, when you do a receive, if the receive buffer is the wrong size, it will say receive buffer too small. MPI doesn't do that in collectives. It could, but the reason it doesn't do it is your typical example is that you're calling a reduction operation on 10,000 processes. You want to add up some data across 10,000 processes. They're all getting together. The reduction operation will be implemented in some clever, scalable way. But if MPI had to check all the things that the receive buffers were the right size, it would spend all its time checking these things, and that would slow it down. So really, the collectives are there for efficiency and ease of use, and checking, like, has the user specified the right receive buffer size, is omitted because otherwise they wouldn't be efficient, and they're really there to be efficient. So you can do a barrier synchronization, MPI barrier. Everyone waits, everyone in the community, now just for argument's sake, let's say we're using Communicaton here, everybody waits for everyone to turn up, and then we carry on. Now, it turns out in MPI, because of the way synchronization works between send and receive, you almost never need a barrier for correctness, but you'll see in the exercise sheet, they're very useful for timing. Timing parallel programs can be a subtle question, because how long does the program take? What do you mean? Which process? Well, if you line all the processes up with a barrier, start the stopwatch, and then at the end, wait for the slowest person to finish, and then end the stopwatch, you get a consistent timing. So, so the barriers are there, but they're not particularly useful in reality. A broadcast is much more useful. At the start, I have not five processes, not 1, 2, 3, 4. At the start of the calculation, this could be the road, and for the sake of argument, rank 1 has initialized the road to A, B, C, D, E, but it wants everyone to know the entire state of the road, or these might be some parameters, the number of iterations and such like. You can broadcast an array, and that means before the broadcast, only rank 1 knows the data. After the broadcast, it's been copied across everywhere. Of course, you could do this with point-to-point send and receive, but it's much more efficient to do it with a collective call. So broadcast is very simple. I've got a buffer, which has got count data types. I have 10 integers, and root says who owns the data. So on entry, the data is on the root processor, which here is rank 1, but on exit from the broadcast, the data has been copied or replicated everywhere. So again, you often do this at the start of a program. Buffer count data type root, com, and in Fortran I error at the end. So you could broadcast 10 integers to everybody. Scatter is actually more likely if I wanted to, if this was the road in the traffic simulation, I might initialize the road on one process and then scatter it. Here I've got one element. I want to say, well, a road of length 5, and I want the first element to go to rank 0, the second to rank 1, which is me, the third to rank 2, the fourth to rank 3, the fifth to rank 4. That in MPI is called a scatter. You have a send buffer and a receive buffer, and beforehand on the root, the send buffer is all the entries are valid, and then it's scattered into small pieces, and so the prototype is very like broadcast, except we have a separate send buffer and receive buffer. We have a send buffer, send count, send type, receive buffer, receive count, receive type. So to implement so send count and receive count, okay, we have to specify. To implement this, what do you think send count and receive count are? So the send buffer is length 5. We want to send one element to each process. I have to specify send count and receive. It's not obvious. What do you think send count and receive count are? Yeah, so the obvious answer, what you would think, is that send 5 and receive 1. That's not actually true. In MPI, in the scatter call, the send count and the receive count correspond to the size of the individual messages. So here, actually, to do this pattern, both send count and receive count would be 1. So that's not what you might think. So I'm doing send count 1, receive count 1. How does MPI know to scatter 5 elements though? Because I've not told it anywhere that there's 5 elements here, not explicitly. How does MPI know that I want to send? I've only said that I want to send 1 element to each process. How does it know that there are 5 processes? Yes, it knows how many ranks. It knows the size of the communicator. So implicitly, it's the size of the communicator, which if it's Commonwealth, is everybody. So that's slightly not what you'd expect. Gather is the opposite. Again, send count and receive count here are 1. We have distributed data or input. Now you might notice that the prototype here has send buff, send count, send type, receive buff, receive count, receive type. But obviously in the gather, this array is only referenced on the root. So, but you have to specify it. It's a symmetric prototype. MPI says that although everyone has to specify a send buffer, so I'll come back to that question. Although MPI in the gather says you have to specify a receive buffer on every rank, it is only referenced on rank on the root. So someone's asked, can you scatter different sizes of different ranks? Yes. The routine is scatter v. It's called MPI scatter v because you specify a vector which gives you the counts. So the default one is that the count is a scalar, and you send the same amount to every destination. But if you want, so the Dilhan's asked a very, I'm going to come back to that. Dilhan's asked a very good question. For scatter v, you have a vector. So you can say I want to send 1 element to rank 0, 2 to rank 1, 5 to rank 2, 0 to rank 3. Does that answer your question, Matthew? Yeah. So Dilhan's asked an excellent question. Shouldn't the send count and receive count always be the same? So yes, if you're doing basic data types like integers, then if the send count is 1 integer, then the receive count should be 1 integer. So absolutely right. In normal usage, send type and receive type are the same, and send count and receive count are the same. However, in MPI, we'll see when we do derived data types, type matching is slightly complicated in MPI. I'll explain that when we come to doing derived data. But you're absolutely right. If you're using basic types, integers, doubles, reals, then send count and receive count should always be the same. Absolutely. So scatter and gather. No, because scatter and gather only. So scatter and gather send small messages, so they'll be more efficient because if this was a large array, if I do the broadcast, if I broadcast that array, then the entirety of the array is being sent to every process. If I scatter it, it depends what I want to do, but if I scatter it, only a small part is being sent to each process. So you would expect that scatter and gather will be slightly faster than broadcast. You could broadcast all the data and everyone just looks at the bit that they need, but that would be inefficient. Does that answer your question? Yeah, I mean, so I think they're different operations. Broadcast takes the same data and sends all of it everywhere. It replicates it. Scatter and gather. Oh, you're saying I see what you're saying. You're saying if I was scattering 5 elements to everybody as opposed to broadcasting 5 elements. Yes, I presume they will be the same. Yeah. I mean, it'll be the same algorithm. I mean, broadcast might be slightly quicker because broadcast is simpler. Actually, broadcast might be quicker because you can probably do more optimizations for broadcast. If I want to broadcast data to somebody, I can give that data to my neighbor and tell my neighbor to send that data to somebody. For scatter, it's more complicated because I have to give them their data and also some other data to say, could you hand this on? So actually, I think broadcast will be faster. I mean, it depends on the implementation, but broadcast is a simpler operation. So I think broadcast in principle would be faster for the same data size. Does that make sense? Because scatter and gather asks you to do a more complicated thing. sending unique data to each destination, which is a harder thing to do. Yeah, okay. So in fact, actually, what we do now, we often do broadcasts and scatters at the start of a calculation and a gather at the end, but they're typically not performance critical. However, every scientific and technical program at some point has to do global reduction operation. You've taken your data, you're doing a weather forecast, you've split the map of the world across lots of processes. They all calculate the local rainfall over their data, but that's a meaningless number. You want to find the total rainfall. So global reduction operations, which we program up by hand, at least with the pi example, should have really implemented are very common. So global sum or product maximum minimum, or you now actually global sum is really the one you do all the time. Maximum minimum you might want to know. You might want to know these if you've got some tolerance. You're trying to converge some iterative algorithm to some tolerance, and you want the error to be less than 10 to the minus 5 everywhere. So you might say, who's got the biggest error? Okay, that's too big, we carry on. But in practice, global sum is the one we do all the time. So there is only one, just like there's one send routine, and you tell MPI, are you sending integers, doubles, characters, bytes? There's one reduction operation, and you tell MPI what you want it to do. So the reduction operation combines data, but you tell MPI, I want to do the max, or the min, or the sum, or the product. You can do logical operations, logical or bitwise. There's also one called max lock and min lock, which doesn't just tell you what the maximum or minimum value is, but who had it. Now, I might want to find out who the oldest person in this class is, and what's the age of the oldest person? Probably me, 54. But I might say, well, who was that? Okay, so that would be max lock and min lock. So they're all there, but in practice, MPI sum is the one which is used all the time. So the reduction operation is a send buff, a receive buff, a count, a data type, an operation, a route, and a communicator. And it's really quite simple, but the one thing that people get wrong, so it's the count which people get wrong, which people don't get correct. So let's have a look here. So this is the example of reduction operation. Here, it's not a brilliant diagram but the count is 4. So what I'm saying is I'm doing a reduction operation on this vector of length 4. Count is 4 here. And what the reduction operation does is it individually does a reduction across each of the elements of the vector. So if count is 4, it performs 4 independent reductions. In other words, it will add together, I'm using a generic operation circle here, but think of it as being addition. It will add A plus E plus I plus M will become the first element here. The second element will be set to B plus F plus J plus N. The third one will be set to C plus G plus K plus O, and the fourth one to the 4. So it does 4 independent reductions across count. The fact that that it's done across 4 processes here is implicit in the communicator. The reduction takes place across all the processes in the communicator. That's implicit. Count is not the number of processes taking part. Count is the amount of data that each process supplies. Does that make sense? So a reduction operation for count equals 4 gives you exactly the same answer as 4 reduction operations of count equals 1. Why should you call the single reduction operation of count equals 4? You would expect it to be faster or slower. So you could do 4 reduction operations with count equals 1 here, but you should always do 1 reduction operation with count equals 4. Much fewer communicators. It's like saying, if I want to buy 4 pints of milk from the supermarket, do I go to the supermarket 4 times and buy 1 pint of milk each time? No, I go to the supermarket and buy 4 pints, because the overhead of the reduction operation is all the communications. It's all that which takes the time. Adding together 1 integer or 4 integers is 1 nanosecond or 4 nanoseconds. It's irrelevant. It's all in the overhead. So a reduction operation of count equals 4 would be, in general, almost probably 4 times as fast as doing 4 reduction operations of count equals 1. So here's a global reduction. We want to do integer global sum. We want to add x and place the result, which is 1 integer, onto rank 0. So we do MPI use. I've got the input is x. I want the result to be result. It's 1 integer. I want to sum them as sum. And 0 says the result is only placed there on process 0. This is the root. This is the guy that gets the result. And across MPI com world, Fortran exactly the same, except I have an error variable here. You can do user-defined reduction operations. I won't cover them here, but you can do user-defined reduction operations. So typically, all the ones you'd ever want to use are in this list. But if you start defining your own MPI data types, and we'll see how to do that this afternoon, if you define your own MPI data types, you might want to combine them. And MPI doesn't. If you might have a way, you might define a structure, and you might want to add two structures together. That might be a well-defined operation. MPI won't know how to do that. So just to say, you can register your own user-defined operations, which then complement the inbuilt ones. But typically, that's slightly more advanced. We typically only would do it if we define our own data types. So I won't cover that here, but it's quite straightforward. It's slightly awkward because function pointers and things are always a bit awkward, but we can do it. Variants of MPI reduce. All reduces no root process. That is by far the most common one. Reduce scatter, the result is scattered. I've never used that one. MPI scan is quite nice. MPI scan is like a reduction, an all reduce, except it's partial. So an all reduce would say that the first entry here is A plus E plus I plus M. The next one is B plus F plus J plus N. And in a reduction operation, it stops. So the reduction operation on rank 0 stops here. On rank 1, you get A plus E. Actually, I need to just double check whether yeah, so it's inclusive by default. I should know that. But so basically, by default, the reduction operation is inclusive. So basically, if I did an all reduce adds A plus this. Sorry, I've jumped too many things here. Apologies. So this all reduce is showing it's like a reduce, but there's no root process. So the answer is available everywhere. So it's just like the reduction operation, but the answer is available everywhere. You should never do a reduce plus a this is functionally equivalent to a reduce plus a broadcast, but you should never do a reduce plus a broadcast. You'd always do an all reduce if that's what you want. And this is so if I want to do an integer global sum, I do MPI all reduce, send buff, receive buff, count data type op. It's just the same as reduce, but I omit the root. So the answer is available everywhere. And in practice, that's really what you want to do in most cases. An all reduced example is just the same here. Now, why you might want to do a vector version is here we might have a local pressure, temperature, and rainfall, which are stored in 3 variables. How do I do that? If I want to add the temperature, the pressure, and the rainfall across all processes, well, I need to put them into a little array. So I'd have to declare an array of size 3 in Fortran, say local data 1 is pressure, local data 2 is temperature, local data 3 is rainfall, and then do an all reduce of them. And then I can produce this. So I'm doing local data to global data. So if you do have your values in separate variables, and you want to accumulate them, it's worth sticking them in a little array like this and calling a single reduction operation with count equals 3 to add all of these together. The same in C. So I realize I think I skipped a slide here. It was the scan. No, so I have the scan. MPI scan. So MPI scan is just like all reduce, except it stops. So rank 0, instead of doing A plus E plus I plus M, it just does A. Rank 1 gets A plus E. Rank 2 gets A plus E plus I, and rank 3 gets A plus E plus I plus M. So a scan is like a reduction operation that stops. It stops at you, and it's inclusive by default, that it includes yourself. And that can be useful in some algorithms, can be useful. That can be a useful operation. I've only used it occasionally. And to be honest, MPI all reduce is the dominant operation in scientific and technical programs. So the exercise, it's exactly the same. Prototype is MPI all reduce, but it does a different thing. That the operation stops at a certain point. So to different ranks get different answers here. So the exercise is actually a very simple one. Having done the global reduction via a message around a ring, you can rewrite it so each process computes a partial sum. Rewrite the message around a ring program to use MPI global reduction. And that's a one-liner. You just call an MPI on reduce. But what is interesting, and you'll see it's in the exercise sheet, is to compare the performance. And you would expect, and you should see, that the inbuilt reduction operations are much faster than doing it by hand, because the message around a ring and the all send to a controller algorithms for computing a reduction all require P messages on P processes, and there's much more efficient ways of doing that. And if you time these, you will see that the on reduce is a lot faster than the orders of magnitude faster for large numbers of processes than doing it by hand. So I'm slightly over by 5 minutes, but I'm happy to take questions. And the format will be now, we'll take a break, and then from 11:30 till 1, William is going to be online. So Dylan's asked, I found the origin speaking. So you have 4 processes. Rank 0 is reduced first by on reduce. Then during the reduction of rank 1, the data of rank 0 would have been written by the reduction of rank. No, so on reduce has separate input and outputs. So an on reduce says I have an input buffer, a send buffer, and a receive buffer, and I have count of them, and I want their integers, and I want to add them, MPI sum. And so here, whoops, I have, where's I'm looking for the on reduce. So every process has input data A, B, C, D, E, F, G, H, I, J, H, and the output, the receive, this first element is replaced by A plus E plus I plus M. This is replaced by B plus F plus J plus N on all processes. So if you do an all reduce, everyone gets the same answer, but the zeroth entry of the receive buffer is the sum of the zeroth entries of the send buffer. The first entry of the receive buffer is the sum of all the first entries of the send buffer. Does that yes, so they're in and out arrays. So that's a good point. By default, you have to specify different in and out arrays. There is a way of doing an in-place reduction. You specify one of these arrays, it will be the send buffer. You specify as MPI in place, and then the receive buffer. But by default, in the default form, you have to specify a different send buffer and the receive buffer. There is a way of doing it in place, but I tend to stick with the more canonical form. Okay. So Matthew's saying in Fortran, an array at the start does not equal 0. You just put the name in, because Fortran, if you just pass the array, it passes the pointer to the first element. So you don't need to do array. It might be more elegant to do array name 0, but when you interface with C and Fortran, just like in Fortran, if you just pass an array, it passes the address of the first element. So that's a good question. Yeah, it's because in Fortran, I'm allowed to do and I can do I'm going to say integer x of 0 to 3 call my routine of x. Even in Fortran, I'm allowed to do I'm actually allowed to do that in Fortran. I can, in Fortran I can do that. I can remap. That's perfectly valid. Just I index it from 0 to 3 in the sender, but in the receiver it indexes it from 1 to 4. That's perfectly valid. But in practice, all it's doing is sending a pointer to the first element. So that's a good question. So MPI request free. So normally you wouldn't need to use MPI request free. So because if you initiate a communication, MPI gives you a request back, and that has taken up some memory. MPI will have to reserve quite a lot of state associated with your message. You then do a wait on it, and when it's waited on, it is the communication is finished and the request is freed and you can reuse it. So once you have a successful wait or a test which is true, then the request is freed up. You could imagine writing a program where some messages you never tested for them, and you might have to free that. You might say, look, I no longer care about this about this communication, so I'm going to free the handler. I'm going to forget the request, and to allow MPI to release that, you can tell MPI to explicitly free it. But that would be an unusual thing to do. So yes, the same can be reused. You know, once you've done a so typically in an MPI program, if I'm doing communications up, down, left, right, and I want to do them completely non-blocking, so I do a non-blocking send up, a non-blocking send down, a non-blocking send left, a non-blocking send right, a non-blocking receive up, down, left, right. I need 8 requests so I have an array of 8 requests. But once I've waited for them all to complete, I can reuse them on the next iteration. So you can reuse them. They're basically they're freed when they're waited on. So yes, you can use the same variable to store them as long as you're careful. Does that make sense? Yeah, you don't need to. Yeah. So once a communication is waited on, MPI said that's over, and it will free up that request, and it will then become. It might even be set it to MPI request null. I don't know what it sets it to, but it becomes invalid after the communication has been. Once you've waited on something, that's that may not be true. Need to check on that. I think once you've waited on something, the request becomes invalid. I mean, some of these a lot of these subtleties are related. You can actually cancel messages in MPI. You can initiate a send and then you can cancel it, but it's very nasty and horrible. I would never recommend doing it. Some of these corner cases and complications happen if you initiate a send and then you initiate an MPI cancel. I don't cover MPI cancel because it's a horrible thing to do, and I've never needed to use it in any real program. So that's. I will maybe check out the subtleties of that. But in a normal program, standard MPI program, you don't need to use request free because it's automatically freed on completion, on test or successful test or wait. Yeah, it's a good question. Okay, so we have slightly overrun, but we'll still get a 20-minute break. So my colleague William will be online from 11:30. Please check that you can run in the reservation. The important point is the reservation I just can't remember what the number is. Oh, because I'm in the 4th line, sorry. I can't find it. It is it's TA020 underscore. Oh, I've slightly messed up that, but that's the reservation. Hash spectrum management equals TA020 underscore 131. So that's our reservation for today, and that'll be running till 6 p.m. I believe, 6 p.m. GMT.